Welcome to Calculus 1. You might or might not have already looked at the trig review lesson. That is not part of the course in terms of your grade. That is just for helping you out with understanding the content. But today we start with our Unit 1 and the notes for it, which starts in Chapter 2. Note that these handouts are located in the Canvas module labeled Handouts, logically. So I basically will just go through the lesson handouts, which basically the whole point of it is to give you notes that are a little bit more organized. So let's start with section 2.1, the idea of limits. Reading here, it says, suppose that you're traveling down the parkway to the shore. You pass mile marker 110 at 4 p.m. and 80 at 4:30 p.m. If we wanted to calculate the average velocity in miles per hour over the course of the trip, how would we informally determine that? Okay, so essentially, for those of you who don't know, the mile markers are on the side of the road. So I've noticed in the past that some students don't even know that, but the mile markers actually correspond to the exit numbers on major highways. So they actually will tell you what distance you've traveled, and of course the times are there as well. So average velocity is essentially in miles per hour, or in other words, miles over hour, divided by hours. So we can actually sort of make an informal guess on the average velocity that the car has traveled by looking at the distance they've traveled and the time they've traveled it in. For example, how many miles have they traveled? Well, if you look up here, they've traveled a distance of, it looks like 30 miles. So 30 miles. And how many hours have they done that? Well, you have to be a little careful here. So 4 p.m. to 4:30 p.m. is 30 minutes, but we want it in hours, so that's going to be a half an hour. So if you do 30 divided by 0.5, or 30 divided by half, you're going to get 60 miles per hour. Obviously, we use MPH to shorthand that, but that's essentially the miles per hour. So right now we have an informal definition of average velocity, is just calculating basically the distance traveled over the amount of time elapsed. So I summarize that, but with more formal terminology below this. It says, the average velocity of an object is clearly the change of what? Of the object over an average elapsed amount of what? So obviously it's over an amount of time, but we use the word distance. In calculus, we use the word position. Okay? Distance is more familiar to us, but we do use the word position to represent where an object has changed in terms of distance. Okay, what you're going to find in this lesson is that a lot of it in the beginning is going to seem very not math-like, maybe even physics-like in a sense. This is, for the most of this lesson, it's going to be a discovery lesson about what we're trying to find. So just note, a lot of lessons we're going to have are going to be purely mathematical. Most of them. It's just this one is a little bit different of a start. So let's look at this example here. It says, suppose a rock is thrown vertically upward from the ground with a speed of 96 feet per second. So just picture yourself throwing a rock straight up in the air. Obviously, you probably want to get out of the way so you didn't get smacked in the noggin, but that's a different story. But let's say we do that with a speed of 96 feet per second. So we're going to ignore air resistance for the purposes of this. The graph here represents the position of the rock, S. We usually use the variable S to represent position, after t seconds. So let's look at the graph and the variable. So first things first. So this graph is represented by the variable S, this y-axis. So this is going to be position. And down here we have the variable t, which is going to be represented by time. So we're graphing time versus position. So this graph, this curve right here, represents the position of the rock over time. So just to be clear, before we even get started with this, because it's a misconception, is that This is not the, as you can see here, this is not the path of the rock. So this is not me throwing the rock here and it's going in an arc position. That's not what this is. This is actually plotting where the rock is. In other words, for our example, the height of the rock over a certain amount of time. That's going to be sort of what the graph is describing. Another important concept here is s equals 0. So s is the y-axis. So s equals 0 is basically right here. So what does that represent in our problem? That represents the ground. Because the person is throwing the rock upwards, they're basically here at that point, and from there you're charting the rock in terms of its height over time. Okay, some other things, just remember, so for time, we can use interval notation to represent how far, what we're plotting this. So if you notice, we're starting at 0 and we're ending at 4. So we've plotted it over the intervals 0 to 4. Remember, we use square brackets when they include the value, parentheses when they don't. Okay, so what's the point of doing this? It says the goal of this problem is to find the average velocity of the rock between any given pair of times. Let's say between 1 and 2 seconds. All right, so on our graph, 1 and 2 seconds are basically located, let's not be misconception here, so they're located here and here. So if we want to find the average velocity of the rock over that time, we are going to have to utilize position and time in order to do that. So it says ideally we would like to plot 2 points on the curve, but we need to know the rock's position at each respective time. Okay, so if we go to time 1 and we plot the point on the curve, we're right here. If we go to plot 2, or time 2, and we plot the point on the curve, we're about right here. Now note, I do have some pre-lines that are marked over here, which represent the position at those times. So the question is how do we find those actual values? Well, this is where this guy comes in. So if you look over here, we basically have an equation for this curve. Now, note that this equation is in function notation. So when I say s of t, I'm saying position, which is s, with respect to time. And of course that is in t. So it's similar to f of x or any of the other function notations you had before, but it's a little bit more informational. But it's position with respect to time. That's the key. So that's your formula. Note that it's negative 16t squared plus 96t. Because it's squared, that means, and that's the highest degree for this, we're dealing with a parabola. And because that term is negative, we're dealing with an upside down parabolic shape, which is clearly what's happening in the diagram. Okay, so it says symbolically, if t sub 0 equals 1, so we're going to represent in this scenario, for example, we're going to have t sub 0 is equal to 1, and t sub 1 equals 2. So the first time is t sub 0, the second time is t sub 1. Then their respective positions would be taking those variables and subbing them into the original equation right here. So hopefully everybody understands, if I want to find the position for a certain time, all I have to do is sub into this equation to find it. So that's what I'm going to do down here. So this is our first position we need to find. So what do we need to do? We need to substitute 1 into our equation up here. So let's do that. So I'm going to write s of 1, because that's my function notation. So it's going to be negative 16 times 1 squared plus 96 times 1. If we do this math, we are going to get 80 as our value. So in this problem, the position is in feet, so we want to be careful just to include that. So just to be clear, before we do any other math, what does that mean? That means if I throw a rock straight up in the air, then after 1 second, it's at a height of 80 feet. That is the key concept here. So what if I want to find s of t1, which is here? Then I need to do s of 2, which means I need to sub in 2 into my equation. So negative 16 times 2 squared plus 96 times 2. That's going to give me 128 feet. So again, what does that mean? That means, well, after 1 second, the rock was at 80 feet, and I measured after 2 seconds, and now the rock is at 128 feet off the ground. So clearly we can, and we end up with 2 coordinates on the graph. We have 1, 80, and we have 2, 128 in terms of our basic work, which represents the y value position after the x amount of time for what we would be working with. Okay, so again, what was the point of all this? If you recall, we want to find the average velocity of the rock, right? That was our goal. And where are we between the 2 times? So if you recall, our informal determination of average velocity here, it was the change of position over the change of time. Well, how can we actually represent that in a formula? Well, first of all, we represent average velocity using the variable v sub avg. Sometimes it's just v sub a, but I like avg a little bit better. It's more specific. But how do we actually determine that formula? Well, it's pretty clear. How do we find the change of time? Well, we need to do the later time minus the earlier time, which is t1 minus t0, which is here. And how do we find the change in distance? We need to do this guy here, which is s of t1, minus this guy here, which is s of t0. We need to do the further distance minus the earlier distance. So if you look at the formula, this is going to be our informal formula, okay, for the average velocity. So this is what we're going to be using in order to calculate it on the next page, which we'll move right on. So what is the average velocity over that time span? Well, we have these values already. We know that the 2 times and the 2 distances, we're going to plug them in. So 128 is the further distance minus the earlier distance, 80. In this case, height we're talking about. And the later time is 2 seconds. The earlier time is 1 second. So we're going to get 48 over 1, which is 48. So we need a label, right? So if we go back to our problem, what was the label actually for our axes? We have seconds for time and feet for position. So we are going to call this feet per second. So we can be very specific here. It says, therefore, between 1 and 2 seconds that the rock is in the air, its average velocity is indeed 48 feet per second. Okay, so this is a very important result. So especially in calculus, also physics, we have found the average velocity for our first average velocity, that it's using a formal definition. But my question is, if we go back to our actual problem here, it says the most important element of this concept is understanding exactly what we just calculated. If you turn to the previous page and draw a line through the 2 coordinates, okay, so let's go here. We're going to go, let's go to our crazy color. So let's say we draw a line through the 2 coordinates. So if I have 2 points on a line, and I do y2 minus y1 over x2 minus x1, what did I just find? Hopefully, right now you have big sirens going off in your head. That is the formula for slope that we've learned that you've known for a very long time. So that actually is a powerful conclusion that we'll summarize in a second. But what I've done for you is I basically summarized the general idea here of what's happening. So change of time here, change of position, change of time, change of position, and then the average velocity being just the line that you draw through the points between any 2 points on a curve. And I'd also summarized a visual of the 48 feet per second that we just did. This is just so that you can look back at this if you ever need to. But what I want to point out here is that this term, so you see v sub av, which is average velocity. They're saying that that is equal to this thing right here. It says msec. Well, you guys remember back from basic algebra and lines that when you do the equation of the line, y equals mxb plus b, m is the slope. So again, here we are, the slope of the line. But they use this abbreviation called sec in the subscript. So what does sec refer to? It's actually from geometry. It's called a secant. So what is a secant line? A secant line is any line drawn through 2 points. You would have learned it in terms of circles. So if I have a circle from geometry and I draw a line through it at any 2 points, then it's called a secant. If you draw a segment through 2 points, it's called a chord. But a secant is called is the line that goes through 2 points. I know there's a lot, but generally we're just doing terminology here. You don't have to know about circles. So the key word is secant. So what that does basically is it creates a sort of a further definition that the average velocity is actually the slope of the secant line through the points. We'll summarize that in 1 second. First, let's try a further example using our average velocity formula. So previously, we went through and we did only between 1 and 2 seconds. Well, let's say now we're going to do 1 and 3 seconds to calculate our average velocity. All right, so a different setup. So over here is the calculation, but we're going to do it on our own here. That's just a summary. So now we're at 180 and we're at 3 seconds on the graph. So we're here and here. So we're looking for if the average velocity has changed or not. So let's use the formula. So average velocity is the equivalent from what we now know of the slope of the secant line. And that is always going to be equal to the position at our further time, which in this case, again, actually, let me just do it as is. So we're going to do s of our further time, which is 3 seconds, minus s of our first time, 1 second, over 3 minus 1. So we already know what s of 1 is. We calculated that. That is 80. Okay, so we need to find s of 3. So remember, how did we do that? We used the equation here, right? And then we plugged in the numbers. So we have to do that again. So basically, negative s of 3 is negative 16 times 3 squared plus 96 times 3. So let's just verify that again. Make sure that's right. Plus 9. Yep. So what do we get when we do that? Well, we kind of see over here what we get, right? We're going to get 144. So what does that mean? We're going to get 144 minus 80 over 3 minus 1, which is 64 over 2, which is 32, remember, is in feet per second. Okay, so we basically have a scenario where we started with between 1 and 2 seconds, we have an average velocity of 48 feet per second. Now we have 32 feet per second. So the question is, hopefully everybody realizes this, is that our average velocity has shrunk. It is decreased. Why is that? Hopefully, again, there are sirens going off in your head. If we throw a rock straight up in the air, what immediately is going to start acting on it? Well, of course, gravity. So our average velocity is decreasing because gravity is taking hold and slowing it down. Okay, so that's kind of the key concept here in terms of what's going on here. And worth noting, if you look at the graph itself, so let me just get rid of some of this in here. If you look at the graph itself, eventually, what's going to happen to it? So the graph is up here, right? Eventually, it's going to start going down. Well, what happened at the top? The rock at some point is going to stop and then start coming back straight down, hopefully not to smack you in the head. But that's why the graph eventually starts getting lower, because the position is going to end up decreasing at some point and end up somewhere back on the ground, which we know is in this case, it's the t-axis, but it's our x-axis. That's sort of the concept that's of importance to what we're doing there. Okay, so let's go back to our trip to the down the parkway here. So what did we do? We informally computed the average velocity between 2 mile markers, right? Well, believe it or not, there's actually 2 major types of velocities. Obviously, the one we just learned, average, but there's another one called instantaneous velocity. Okay, with the crazy spelling right here, instantaneous. So what does instantaneous velocity have to do with? It basically constitutes the exact value on your speedometer at any one moment. So when you're driving and you look down to check your speed and you see 38 miles per hour, let's say if you're on a back road, or once again, if you're 64 or 63 on the parkway, 67, you're basically, that one moment is your instantaneous velocity. Believe it or not, that is also a very important type of velocity that we'll be dealing with. Now, here's the issue. Let's say we took our average velocity and we tried to use it to calculate instantaneous velocity. Well, think about our rock example at only t equals 1. So remember, instantaneous velocity is at one time. If we actually tried to utilize the average velocity formula and we plugged in just one time, s of 1 and 1 for our t's, we would end up with this crazy looking thing here. Now, hopefully everybody realizes that we have missing variables here, 2 of them. So there literally is no way that we're going to use the average velocity formula to calculate instantaneous velocity. The idea here is that we're going to need a new strategy in order to compute this value. And that's what leads us to the important calculus concept right at the beginning of our calculus unit here. Okay, in order to get there, though, let's take a look, first of all, at some of the calculations that we've already done. Or let's start with one calculation. So look at this output. So what I did was I plotted time versus average velocity. So this is not time versus position. It's time versus the average velocities that we have calculated. So if you recall, our first average velocity that we computed for our rock problem was between 1 and 2 seconds. There's an average velocity of 48 feet per second. So we did that mathematically a couple pages ago, right? So the strategy that we're going to use in order to compute the instantaneous velocity is to take smaller and smaller intervals and calculate their average velocity. Now, we're not going to do it manually because takes up too much time, but let's just look at the logic. So we already did our first value here. Now look at this one. So I am now between 1 and 2 seconds. I'm now between 1 and 1.5 seconds. So I have shrunk my interval by 1/2 second. And according to that, if I go from 1 to 1.5, I am going to get an average velocity of 56 feet per second. Now, how is that calculated? Again, remember our formula right here? This guy? So instead of putting 3 or 2 or 1 that we did before, we would put 1.5 in for the variable, and we would get 56 feet per second. So let's shrink that even more. We're going to go to 1 to 1.1. What do I get? 62.4. 1 to 1.01. 63.84. 1 to 1.001. So hopefully you get the point that what are we doing? We're shrinking the span so that we are getting as close to 1 second as humanly possible without actually being just 1 second. So before we get anywhere with this, what I want to do is I want to show you a visual of this. So again, look at our rock example down here. So our initial calculation was from 1 to 2. So our line here, 1 to 2, 48 feet per second. So I shrink it to 1 to 1.5. So you can see these are going inwards right now, and I'm getting 56. Now let's shrink it again. So going in, we're now to 1 to 1.1. What is happening here with these points? They're getting closer and closer to one another, and what do you think eventually is going to happen? They're eventually going to be just 1 point right on top of each other at t is equal to 1. Okay, that is the concept that we are dealing with this whole thing. But before we get there, if you're looking at this, you can see what I want you to do is I want you to analyze what's happening to these average velocities. Look at the values themselves. So between 48 and 56, that is a distance of 8. Between 56 and 62.4, we're at, I think, 5 point something. No, 6.4. Between 62.4 and 63.84, now we're at 1 point something. Now between these two, we're barely at a tenth around there. And then look what's happening. It's shrinking. The numbers appear to be approaching a value. What value do you see that they are approaching? Hopefully, again, you are staring at this going, Jesus, it looks now that this 9 is just going to repeat, which means this sucker is heading towards 64 feet per second, which is our value here. And what did you actually just find? Well, what is the title of this section? It's called limits. And what you just found was your first limit. Okay, so a little bit of terminology here. So if we were to be very specific, I'm going to read this because it's very technical. It says, we will introduce limits more formally in the next section, but essentially this calculation in the problem for finding instantaneous velocity boiled down to finding the limit of the average velocity as the time approaches 1. So finding the limit of the average velocity as the time approaches 1 second. Because that's what's happening. It's reaching 1. So in terms of what you'll be learning in this class, basically this is the formula for instantaneous velocity, and this is the terminology for limits. It's LIM for limit as t with an arrow approaches 1 of our average velocity. Right? We'll be going through that in a lot of detail in the next section, but for now, I'm just giving you a brief intro of what that's going to look like. So let's talk about sort of a summary of that whole thing. So right here. Okay, so two important things are happening. So the secant lines approach a unique line called a what line? Okay, so you ready? So look at this sucker here. So all of these lines here are secant lines because they're intersecting in 2 points. So they're intersecting the curve in 2 points. Now, what do we call a line that intersects a curve or a circle in 1 point? So you would have learned it as a circle like this. It's one of the more famous terms in mathematics. It's called a tangent line. Okay, so what does that mean? That means the slopes of the secant lines approach the slope of the tangent line at t is equal to 1. Therefore, we can basically express the slope of the tangent as the limit of the secant as t approaches 1. So I know there's a lot of technicality here, and students sometimes drown in technicality, but that is what's happening. So right now we have secant lines that are, as the points get closer together, they eventually form a tangent line. So what is the instantaneous velocity? It is, believe it or not, the slope of the tangent line. That's it. So if we can find the slope of the tangent line, it is the instantaneous velocity. And just to summarize here, we can say that just from what you're trying to get out of this section, by the way, or the most important elements of the section, essentially the average velocities approach the instantaneous velocity, Okay, so what are the average velocities? They're slopes of secant lines. So analogously, the slope of the secant lines will approach the slope of the what line? Well, what's analogous to instantaneous velocity? The slope of the tangent line. So right here is basically the summary of the entire section. Those are the things that are important. Now, you got to know the mathematics, of course. But in terms of understanding limits and velocities, this is the most important thing that you're going to get out of this section. Okay, that being said, just like I mentioned, you need to be able to figure out problems that will come up in these sections. So as you go through your MyMathLab homework and you go through the labs from class, or if it's in a remote environment at home, you're basically going to need to do application problems, which is what calculus is about. So in this standpoint, you just have to be able to read a problem and understand what they're asking. So that's what we're going to start with, number one. And by the way, I do a ton of examples. I know it didn't seem like it in this lesson. This is actually a rare type of discovery lesson, but normally I teach by a lot of examples. So just realize that they'll be coming. It says the position of an object moving along the line is given by the function s of t is equal to negative 7t squared plus 63t. Find the average velocity of the object over the interval 1 to 3. Okay, so this you should be able to eat for lunch based on what you learned in class. Why? Because it's identical to the rock example. So we have an equation that maps out how the rock is actually going to progress in terms of its height. And in this standpoint, we have, in this case, it's just the position of an object. So now we want to find the average velocity over the interval 1 to 3. So what is the formula for average velocity? Well, we want to take basically our later time, which is 3. We want to subtract our earlier time, which is 1, but as evaluated as position. So S of 3 is the first position, S of 1 is the second position. Then we want to take the actual times and subtract them. This is the main formula for average velocity. So how do we do that? Well, if you want, we can do it all in one formula, or we can do an aside like we did last time. For example, we're going to need to know what S of 1 is. So what is S of 1? Well, we're going to put 1 in here. So how do we do that? Negative 7 1 squared plus 63 times 1. What do we get? We get 56. S of 3, we need to do the same thing with 3. We need to take 3 and plug it into our equation. We're going to get 126. So this allows us right away to do 126 minus 56 over 3 minus 1, which is 70 over 2, which we know is 35. Basically, we don't have a measure here. I always forget to do this, so we'll just put it in here. So let's put an add-in here in feet per second, just to make it so that it is familiar. So we'll say feet per second. In an exam situation, I would put it in. I just forget to put it every year. So 35 feet per second is our average velocity. You should be able to handle that in a calculus class. You should be eating that type of thing for lunch. These are the easier problems that you'll get through. So what about 2? It says return to number 1 and find the average velocity of the object over 2 to 2 plus h. Okay, so this is where the warning signals start coming. So now we're into algebra insanity. So what they're saying basically is, I want to start at time 2 and I want to end up anywhere. So what if I want to add, let's say h was 3 in this problem. So that would calculate 2 to 5. If h was 10, it would be 2 to 12. I want a formula that allows me to start at time 2 and find any resulting time. So what that means is the answer is going to have the variable h in it, and it's going to be a formula instead of a number as an answer. But how do we do that? Well, the same thing. How did we do the last time? We still need to use the same formula. Say v sub average. Our later time is 2 plus h. Our first time is 2. And our times are 2 plus h minus 2. Now, I put it in parentheses on purpose because we want to make sure the algebra plays out okay. So in order to do this, we need to go through the process. So, well, s of 2 we haven't found yet. We can do that. So s of 2 is negative 7, 2 squared plus 63 times 2. That is going to be equal to, it looks like, 98. But s of 2 plus h is a whole nother story. I need to take 2 plus h and I need to sub in to both of my missing spots here. So I'm going to move over here because we need some work. So a couple things. So most of you are going to obviously realize this is distributive property, but we have a whole different scenario over here. So when I do 2 plus h squared, that is absolutely not equal to 4 plus h squared. Okay, if your instincts are off the deep end, basically, if that's what it is, we try to get away from that and burn that into people's heads in pre-calc and algebra. So what do we have to do when we see 2 plus h squared? We have to FOIL. So when we FOIL, we get 4 plus 4h plus h squared. Okay, by the way, the outside and inside are both 2 h's. I just shortcutted the process. So what we're going to do in our problem here is we're going to replace, so it's negative 7, we're going to place, let's rework it so that it's in the trinomial order that we're used to. I'm going to do that, and then again, I'm just going to copy this because we'll do the distributive property in the next step. When we distribute, we get negative 7h squared, minus 28h minus 28 plus 63 times 2 is going to be, it looks like 120. So yes, 126. Sorry about that. I was distracted by my dog. Jumped on my lap. 126 plus 63h. So we're going to get negative 7h squared plus 35h plus 98. Okay, so what was the point of this? Remember, we're calculating these guys, which are this and this, in order to get them back into our average velocity formula over here. So that's exactly what we're going to do. We're going to get negative 7h squared plus 35h plus 98 minus 98. This is 98, this is the trinomial, so it's basically this minus this, over, so 2 plus h minus 2 is, interestingly enough, just h. Alright, another interesting development is here, you look up here, these guys are actually gone, so what do we end up getting? So we're going to get negative 7, hold on, negative 7h squared plus 35h over h. Okay, so if you look at that closely, every single one of our terms has an h in it, which means we can cancel one out. And we're going to get this as our answer. Okay, so negative 7h plus 35 is the average velocity in this problem. So I just want to point something out. So if you're looking at this formula I mentioned, so if I want to know what the average velocity is from 2 to 5, what does that mean h is? It's 3, which means I would take 3, plug it in here. I would find whatever that is. It looks like negative 21, which means we're going to get 14, which means the average velocity from 2 to 5 is 14. So what is this doing essentially? This is creating a formula for any scenario where we start at 2 seconds, which is a pretty neat concept, but that's basically what we're doing by doing something like that. But it's a good start with some heavy algebra. Okay, so why don't we move through this one for number 3 here. We'll go through this a little faster. It says, for the function 6x squared, make a table of slopes of secant lines and make a conjecture about the slope of the tangent line at x equals 3. Okay, so whenever I do this in class, students usually have an okay time here because it's something similar to what we did, but once we get to the whole secant line business, For whatever reason, it's just not always there. So let me do the best to kind of explain. So once again, not only did we learn that the average velocity approached the instantaneous velocity, we learned specifically that the slope of the secant lines approaches the slope of the tangent line. So how do we determine the slope of the tangent line? Not directly, but by using the slope of the secant lines at smaller and smaller intervals. So for this problem, we start from 3 to 3.1 second. So they want to know, what do we find here? We need to find the slope of the secant line. Now note, what is the slope of the secant line? All it is the average velocity. Well, we have a formula for that. Our formula is take the later distance, s of 3.1, minus the closer distance, s of 3, or height or position, whatever you want to say, over 3.1 minus 3. So if we do this calculation, I'm not going to do it out like I normally do. You should be able to figure this out by plugging it into 6x squared this time. So 3.1 squared times 6 gets you this over here. And 3 squared, which is 9 times 6 is 54, would go here. You would do all of that math, and what you would get is 36.6. I recommend, at least for the first one here, that you do the calculation so you understand where it came from. So what do? We're now going to a smaller time span. So what are we mimicking? We're essentially mimicking this chart right here, right? So what are we doing by doing that? We're creating a limit by seeing how the values are, what value it's getting close to as it approaches where we need to go. So here, what are we doing? We're doing s of 3.01 minus s of 3 over 3.01 minus 3. If we do that calculation, we're going to get 36.06. If you want to check that by plugging in to 6x squared, the top of these, that's fine. If we continue to keep doing that, hopefully you see the pattern that's developing here. We're going to get 36.006. If we do it again, we're going to get 36.0006. And yes, it'll keep on going like that. So we know these are the slope of the secant lines all the way across. So the question is, as we shrink the time spans from here to here to here to here, we are getting closer and closer to the slope of the tangent line. So what value are we approaching here? It clearly is approaching 36. So that makes 36 the slope of the tangent line. Okay, so that wraps it up for the first section. We'll be getting more into the technicalities of limits in the next section, but that's a good place to start. And you'll have some problems that are very similar to the ones you see here in your homework and labs.